this video we'll be looking at integration. So, integration is a method of finding the area under a graph, or actually in between the graph and the x-axis. It's also the inverse operation of differentiation. So, for any rational number, the integral of x, that's the integral sign, the integral of x to the power of n equals x to the power of n plus 1 over n plus 1. So what you do is add the power and divide by that new power. Okay, so actually one last thing I forgot to mention is because it's the inverse of differentiation, you don't know if there's a you don't know what the constant is, because for example if you differentiated this, the plus c, which is a constant, would disappear. Okay, so I'm gonna prove that I'm gonna prove the integral of x squared, our old friend x squared. Right. Okay. Alright, so let's just draw a little graph here. So what we can do is actually have a number of rectangles to estimate the area, and then let n approach 0. So the integral of x squared is equal to the area, and the area, we're going to define the endpoint of this as x, by the way. So the area is equal to 0.1 squared plus x over n squared plus 2x over n squared plus, and so on, and then this is multiplied by x over n. Okay, so what this is x over n times by x squared over n squared plus 4x squared over n squared, and so on, right? So you can just take the n squared out, and actually you can also take the x squared terms out, so it's actually x cubed over n cubed, because it's multiplied by this, plus 1 plus 4 plus 9. And this might look a bit familiar. Is that the same as saying, oh right, this is an interesting result. So it's actually using summation now, and we can see that this is just the sum of the square of natural numbers, sum of squares of natural numbers. So let's actually go left now. Apologies. So the area is x cubed over n cubed times by 1/6 n plus 1 times by 2n plus 1. And then this n, so this n is the same as these ones. We're just going to have to expand the brackets a bit here. So this is 2n cubed plus going to have to do a bit of rearranging here. So it can just be x cubed times by a third, yeah, just a third actually, plus a half n. No, apologies, it's actually 1 over 2n. Let me just get the rubber here. 1 over 2n plus on to 1/6 n squared. Now, it's actually we're going to take the limit process, and we're going to do another limiting process here. So by letting n approach infinity, the area is equal to x cubed times by a third. So here's our result, and therefore by letting n approach infinity, the area is actually equal to this function, which is x cubed over 3. Another feature of integrals is that they can be improper. This is where the integrand has no proper value at one of these limits. So for example, 1 over x, actually both of these limits do not work, because as 1 over 0 is also it's undefined. The integrand, which is the expression being integrated, that's where it's undefined, and that makes it an improper integral. So why don't we try and take the integral of 1 and 0 of x power minus 2, 1 over x squared, as another way of saying it, is improper, as at 0 1 over x squared is undefined. So just using the laws of integration, plus the power and divide by the new power, that equals minus x to the power of minus 1 with the limits 1 and 0. That's how you write the limits, by the way. That's the notation for limits. So that's equal to minus 1 to the power of minus 1 minus 0 power of minus 1. So you may see a bit of a problem here, as the value of x approaches 0. X to the power of minus 1 approaches infinity. So therefore, the integral of x squared at the limit, that's meant to be 0, is actually undefined.